Hello class, today I'm going to show you how you can evaluate the accuracy of your mesh. Let's start with workbench. Okay, let's see what type of geometry I'm going to investigate. I already drew this geometry, so it is 10 millimeter thickness, 400 millimeter depth and 1000 millimeter length, and we have a 200 millimeter diameter hole inside it. 100 kilonewton force is applied for left and right side. Let's draw this geometry. Again, I'm going to do static structural geometry and opening space clay. Okay, space claim is open. Let's see. I'm selecting XY to draw a rectangle. (400 by 1000). 400 millimeter tab 1000 millimeter. Okay, now I'm going to create a hole at the center. From this, so it is going to be 500 and negative 200, and the diameter is going to be 200 millimeter. Okay, now it's time to pull. What was the thickness? 10 millimeter. Let me check it once more. But as you can see, this is a large geometry, and if you want to take advantage of the mesh size we can have for academic version, we need to use symmetry. Okay, let's see. I'm going to create a plan parallel to this surface. So click this plan. Use move item. And what is the distance? It should be 500. Done. So I have a plan 500 from this side, which is going to be at the center. And I'm going to create another plan here. And move it 200 to the center. As you may remember from the previous tutorial, we can use split body. Select the solid and the cutter. Cutter is going to be this plan. And also I'm going to select this. Oh, let's get rid of this side because we don't want it. Also this surface. Now I'm going to select again, and as a cutter this time this surface. Now let's turn up the split body. Now I have another surface which I don't need. As you can see here, I'm using the quarter of this geometry. I can have one more symmetry condition which is going to be at the center of this layer. So to create that, I'm going to create another plan here, move it 5 millimeter to go to the center of this layer. So I'm cutting the half of this layer. So let's go again to the split body, select the geometry. Now it asks us to select the cutter. Now I select the cutter. Let's get rid of this one. So I minimize the amount of geometry we need to analyze. Okay, we're done with this geometry. Let's open model. If you remember, we talked about frictionless support, and I said we can use frictionless support for symmetry sections. So for this case, I'm going to use frictionless support for the area or for the surfaces I cut it to have symmetry. Okay, the first one, it is going to be, let me select the structure, static structural support, frictional support, because we already have half of it the other side. Also we have this part. And another symmetry surface here, which is going to be frictionless support, which means we don't have any movement vertical or perpendicular to that surface. What about force? Let me go back to the force. So it has 100 kilonewton. So I cut it to the half to have 50 kilonewton, and then again another half to get 225 kilonewton. Sorry, sometimes people talk like that. So I'm going to apply here a load force which is going to be quarter of the original force, 25,000 Newton, and I'm using vector which is going to be the perpendicular to that surface, and I'm happy with it. Let's go with the default mesh. Add some solutions and solve it. Okay, as we can see here, with this coarse mesh, the stress concentration area is about here, and it's about 106 megapascal. But this calculation is based on this coarse mesh. What if we have a finer mesh? And how fine we need to go? When we can accept the result of our finite element analysis as an accurate result. To check the error, I'm going to add error case here, insert. So you right click over stress, use insert, and find error. Let's solve it. Okay, what this shows the amount of error we have here. Usually if it's less than 0.1, we say it's acceptable, not too bad. All of them are under 0.1, which is good. But the highest error we can see here is about here. If we go back to the stress, it is exactly the area of stress concentration. So we have more error here. How this error is calculated? This error is calculated based on the energy formula we have for finite element, and higher error is the area with the highest difference from the smooth results. So based on the ANSYS calculation, we have highest error close to this area, which we know it is for stress concentration. If we increase the mesh size or decrease the mesh size, are we going to have larger stress or here or smaller? Let's investigate this one. I'm going to change relevance. Currently it's 0. What if I go to negative 100? Let's solve it. The mesh is very coarse. Let's check the stress. Stress decreased, 102. Previously it was 106. But still stress concentration is about this position at the tip, which we expected. Let's check the error. The maximum error is around here, and it's about 1.5, which is not acceptable. It's very high, we can't accept. Let's go back to the mesh and increase relevance to positive 100. Now we're going to have a little bit finer mesh. Stress 107.1. The maximum stress increased from 106. What about error? The maximum error moved to this area, and at the area of maximum or stress concentration, the amount of error we have is very small, 0.001, which is very small number, and it's it may be acceptable for us. So using this structure error, we can check the amount of error we have because of the finite element analysis. Okay, let's delete this one. Right-click over stress and go for convergence. Let's change allowable chain to 1. And click on solution. For maximum refinement loop, let's select 4, which means it is going to repeat the calculation 4 times. And refinement depths, which means how many mesh this refinement is going to affect. Currently it's 2. I'm going to keep that 2 mesh. Let's solve it. So here, ANSYS is going to investigate convergence. Let's see the stress. Oh, everything is different. By using convergence, ANSYS came here and find, okay, we have high stress here, and start to repeat making this mesh finer at least 4 times for at least 2 mesh size. It was, for example, here and here there was a large mesh here, and it continued this till reaching convergence. And now we can see the maximum stress is 108, which should be much more accurate. Let's check the convergence. What this shows, after second time loop, we reached to that 1% allowable change, and it didn't continue anymore. So if I change this to 0.1, by the way, let me add error here too. Okay, let's solve it. This time the criteria is reaching 0.1%. So the number of iteration and loops ANSYS need to refine mesh would be a bit more than 2, which we had for the previous one. Okay, ANSYS finished solving it, and let's check the stress. Still it's 108. Stress concentration, the mesh size around the stress concentration is much more finer, and ANSYS at least repeated this process 4 times to reach this convergence, and convergence criteria was 0.1%. Let's check the convergence. As you can see, it repeated till reaching this number, and each time ANSYS decreased the mesh size, the number for the equivalent stress reaches 108, and the change decreases, and kind of we are converging to this number. So 108 is accurate number, and as you can see in this table, at the early stage we have almost 1% change, and then 0.5% change, and then 0.1%. For the fifth time it's much smaller, and the elements numbers increases. Let's see the error here. We don't have that much error, or the error for the stress concentration area, which is the area of interest. We don't care about this part because we already know we don't have that much stress here. The error for this area is very small. Even the maximum error, if you check, it's 10 power minus 6, so it is so small error. Let's change the number of loop to 4, 5 or 6, and an allowable change, which it is a criteria for this part. Let's go for 0.01. So the accuracy of result is going to be much more higher, and this calculation won't stop till reaching this criteria or reaching this criteria 6. It is going to repeat 6 times. If we reached that criteria, it is going to stop earlier. If it didn't reach this iteration, it is going to repeat it 6 times. Let's solve it. Okay, it seems the criteria we selected is very small for ANSYS, and the number of mesh may increase. So let's keep this 1.1 and change the solution to 7 times, and depth 2 would be enough. Now let's solve it. Okay, I don't know why, for some reason ANSYS didn't want to solve without clearing the data. So right click over solution and clear generated data. Now we can start solving with the new input. Solution would be 7 times the number of refinement loops 7, refinement depth 2, and convergence 0.2. We can see that gradually these loops, ANSYS doing these loops, and the number of elements increases, and it already reached 0.2%, which we allowed here. So it just needed 4 times refinement to reach that 0.2%, and the result is 108, and it didn't need to repeat that the number of loops 7 times. Let's check the error. Still very small error. Stress 108.7, and this convergence can be seen. If we selected very coarse mesh, it is going to be a little bit lower, and by increasing the number of mesh, it converged to 108. Let's see how was our hand calculation. If we find nominal stress from ME2525, force, which is 100 kilonewton, divided by the area without considering this whole. So the area is 400 millimeter minus 200, diameter of this hole times the thickness 10 millimeter. So the nominal stress is going to be 50 megapascal. Now we need to calculate the stress concentration. For stress concentration, you need to know the stress concentration factor, Kt. Let's check it from the diagram. If you check, for example, I found this diagram online, you need to find it from the reference books. The numbers we need is diameter of the hole and the this dimension of this geometry. So d over this d. We need to find this number. Let me go and check it. D over b, which is the 200 over 400, which is going to be half. For half, if this ratio is half, we come and find Kt, which is a little bit above 2.15. This part is 2.2, 2.1, 2.15, for example. So I selected 2.15, and to find the maximum stress, I multiply nominal stress to stress concentration factor, 50 megapascal times 2.15. It is about 107, which is pretty close to the number we found for stress, 108. But whenever you are doing analysis, you always need to do a little bit of hand calculation to know what range of number we expect to find. The hand calculation shows 107. Your coarse mesh, it was around 102, and then you refined it, reached 106, and by doing convergence study, you find the results by refining mesh tends to reach 108, which is pretty close to your hand calculation and acceptable for the as accurate results. Let's close this and save this study. Thank you very much.